Thanks, Prof. Man, for the nice introduction, and thanks for providing the inspiring talk. My talk is a little bit specific as compared with Prof. Ni's talk. Just now, Prof. Ni mentioned about several R, recycle, reuse, remanufacturing, and focus on remanufacturing, but mentioned about the recycle. I think about my talk is a little bit related to Prof. Ni is the reduce. Reduce what? The aim for our work is reduce the carbon dioxide. So how to reduce the carbon dioxide? We use the electrochemical approach to try to produce some chemicals and fuels to reduce the emission, reduce emission of carbon dioxide and reduce the consumption of fossil fuels. So the topic on my topic today is the electrochemical manufacturing of chemicals and fuels. I'm from ME department of PolyU. So for some chemical production, we normally use some large equipment chemical engineering approach. When we mention about chemical engineering approach, in our mind, the first impression is like this one: this large equipment in certain places, and it will also emit a lot of carbon dioxide and a lot of exhausts. So we want to reduce some the emission of carbon dioxide because it's not in line with the carbon neutrality aim. So for the carbon neutrality aim, actually there are two kind of issues. One is carbon emission, and the other is the carbon reduction. So this is for carbon neutrality. Normally, this is the balance for carbon emission and carbon reduction. For carbon emission, actually, mostly for previous years, is normally based on the consumptions of the fossil fuels. So to realize the balance for carbon emission and carbon reduction, so we should reduce the carbon emission first. So in recent years, actually, the electrochemical approach have been well developed to try to use for produce some chemicals. As compared with the traditional chemical approach, the electrochemical approach has a lot of advantages. The first one, it is very small, right? This is very small as compared with such kind of large equipment. So this small device can be used for on-site production. For example, if we were to use some hydrogen peroxide, we can use such kind of device in our home and produce hydrogen peroxide for disinfections in our home. But for the traditional approach, normally we need long-term transportation. We need high cost for the transportation and so on and so forth. Especially for some chemicals, such as in Hong Kong, there's no such kind of industries to produce some chemicals. So we need transport from mainland, from Sichuan province to long-term distance will give a high cost. So electrochemical approach has such kind of advantages. And the other one is the electrochemical approach use some renewable energy, such as solar energy and wind energy, and there's no CO2 emissions. It's a clean process. Especially recent years, actually the green energy or sustainable energy has well developed, and the price for the renewable energy has decreased a lot. We can see it is supposed that after 7 years later, the cost for solar electricity can be decreased to 3 cents US dollars per kilowatt. So which means actually this price is actually lower than the price produced from the fossil fuels, which means we have a lot of clean electricity to use. But in our daily life, we cannot only rely on the electricity because we also need some chemicals. We need some hydrogen gas for drive something, or we need some chemicals for ethanol, methanol, or some hydrogen peroxide for such a kind of chemicals. So how to convert the clean electricity to fuels? So we need the energy conversion. We need an energy conversion process to convert the electricity to chemicals. So my research group actually established only 1.5 years. So some of the work my work mainly focus on the electrochemical approach to convert some earth-abundant simple molecules to some chemicals, focus on CO2, oxygen, and water, and nitrogen. So for CO2, actually, we use CO2 to produce some chemicals like ethanol, methanol, and we use oxygen to produce hydrogen peroxide to disinfection. For oxygen to hydrogen peroxide, actually, this is a wave to because of the COVID-19, actually, we start this work to try to produce some hydrogen peroxide for disinfection. And from water to hydrogen gas, actually, this is a very emerging technologies for produce hydrogen gas. So this is a general introduction for the research in our group. But for the clean energy conversion process, there are some challenges. There are some challenges because previously in the lab scale, normally it's in very small current density. It's in small current density, but for the industrial requirement, normally it need large current density and long-term stability. So for this requirement, 100 milliamp per centimeter square over 100 hour stability, this is the minimum requirement for electrochemical approach. For example, for hydrogen production, normally this one should go to the requirement must go to the 500 milliamp per centimeter square over 1000 stability. But for CO2 conversion, normally this requirement is 100 milliamp per centimeter square over 100 stability. So this is the but now actually this requirement actually for most studies is still limited in lower current density and low stability. So two factors actually limit such kind of development. One is the electrocatalyst, because electrocatalyst normally determine the stability, determine the ferrotic efficiency or selectivities for the for such kind of reactions. And the other one is the chemical reactors. The two factors limit such kind of give such kind of challenges that we should demonstrate. So in previously, we also focus on these two parts. One is catalyst design, and the other is chemical reactors development. And try to based on this kind of the middle is the chemical reactors, and we try to produce some catalyst and convert to some valuable chemicals and fuels for our daily life. So for the catalyst development, normally especially for electrochemical process, there are some requirements. First, we should have more active sites to give more activities for materials. So we need to change the materials through the change the materials by construction of the materials. The first way is try to decrease the size of the materials. If the size is decreased, so the active area or active size is rich, so such kind of material will give more activity or high current density. And the other way is to give a proper electronic structures to increase the intrinsic activity of the catalyst. Let's take an example of by using the hydrogen production rate. For hydrogen production, normally there are two protons first go to the catalyst surface to form such kind of intermediate. This intermediate is very important. So this intermediate should not the interaction between the intermediate, between the catalyst should not very strong or very weak. If it's strong, these two intermediate will not leave to form hydrogen. If it's too weak, this intermediate will go back to two protons, and there's no hydrogen gas was produced. So the two ways are used to produce the catalyst, which is to enrich the active size and also to give a good or proper intrinsic activity for produce some chemicals. So previously we did some materials, and the first one is try to reduce the size of the materials. So we produce some two-dimensional layered small size, several nanometers nano crystals to produce some chemicals. And this is for several nanometers for produce hydrogen gas. And then recently we also thinking about try to reduce the size further to from several nanometers to single atom catalyst to produce hydrogen gas. so as an example, so this work was published several years ago, and this one actually we combine the lithium-ion battery with the catalyst. That is, we use the layered materials as cathode, and the lithium can destroy the materials, and then we produce small sized and amorphous nanomaterials. And after the lithium treatment, we can see the materials changed from the bulk crystal to several nanometers and become amorphous. Amorphous materials normally have rich active sites. So we tested our performance and comparison, actually we can see that the activity or the small nanomaterials is much better than the original large materials, and also no matter for the overpotential and the Tafel slope, also better than the original crystals. And the hydrogen evolution activity was greatly improved. So, but even though the performance is improved, so we are still thinking, is it possible to further improve? Because the activity actually is still lower than the commercial platinum carbon catalyst. So we think about, is it possible to further improve the activity and further enhance the performance? So we also focus on the two-dimensional layer nanomaterials because it has a lot of structures. So we were to, based on the structures, to design some materials to further enhance the performance. Recently, we further decrease, we based on this concept, so we further develop such kind of catalyst. We use the palladium sulfide as the substrate and grow some single atom catalyst to further decrease the size of the nanomaterials to single atom catalyst on the two-dimensional layer nanomaterials. So after we get in such small single atom catalyst, so we first test the intrinsic activity of the catalyst by using the floating electrode. The floating electrode actually eliminates the limitation of the mass transportation. So we can see our materials, actually the intrinsic activity is much better than, not much better, it's better than the commercialized platinum carbon catalyst. And also the mass activity actually is also higher than the commercial platinum carbon catalyst. And also we tested this performance going to the 2000 amp milli per milligram. So this is very high current density. And also as comparison, our materials actually is also better than other reported catalysts as well as commercial or platinum carbon catalyst. So this is a lab scale industry investment because there's no mass limitation, but for a real case, we need to go into the solutions. So we also tested the samples in the in H-cell. So in H-cell, we also see that our materials is also better than the commercialized platinum carbon, and also the mass activity is also better, which means in lab scale or in fundamental study, our materials are both better than the commercialized platinum carbon. And also, we can also, if we go to the 2000 milliamp per centimeter square, the difference between our catalyst with the commercialized platinum carbon, the difference is much bigger. So which means our materials performed good performance in high current densities. So and then because now I'm in the mechanical department, so I want to give a good testing for such kind of device. So we built such kind of PM device to further test and comparison our catalyst with the commercialized platinum carbon. So actually, so we can see in the real device, our catalyst is also better than the platinum carbon commercialized catalyst. So we can see at a certain current density, and our cell can give a low voltage. So this is some examples for our recent work on hydrogen production. And in addition to hydrogen production, so we are thinking about, is it possible to use oxygen or nitrogen in air to in a practical scale? Because in our daily life, not only water but also we have a lot of oxygen, we have a lot of nitrogen or nitrate. So we can use such kind of resources or earth abundant resources to for practical use. So for oxygen utilization, normally previously the oxygen is used for fuel cells because it's 4 electrons to produce fuel cells. But recently there's another way, is 2 electrons to produce hydrogen. What we want to study this work is because of COVID, frankly speaking, because hydrogen peroxide is very important. Actually, is not only in paper treatment, in chemical synthesis, and also in disinfections. In some industry, actually, the hydrogen peroxide vapor is used to disinfection our N95 mask. So actually, when the COVID-19 start, actually the hydrogen peroxide is the consumption, the need for hydrogen peroxide is greatly increased. So we want to use electrochemical approach to produce hydrogen peroxide. But there are some challenges for oxygen reduction towards the hydrogen peroxide. First, in lab scale, normally it's small current density. It's only 5 in lab scale, only 5. The small current density means the production rate or the production concentration will be limited. And also the selectivity is limited because the oxygen can first go to the hydrogen peroxide, and then hydrogen peroxide can combine 2 electrons and then go to the water, which means the hydrogen peroxide, the selectivity will be decreased and mostly from the water is not our product. And the other is the cost is high. So due to this challenges, so we first test the samples. We use the carbon because carbon is cheap. We can purchase it very easily. So we first test the carbon performance in the acid. So we find that at a small current density is 5 because most work reports that kind of phenomena in small current density is 5. We can go to the selectivity, can go to the 17, almost 17. But if we increase large current density, we can see the selectivity decreased a lot. So which means if we were to go to the industrial scale, so such kind of performance cannot meet the requirement. Then we develop a method. So we add a small amount of ions because the sodium ions is very normal. We can use in our daily life from salt, from other wares. So if we introduce only 5 millimole, very small amount of trace amount of sodium, so we can see the selectivity or the activity both are improved. As comparison, we can, if we go to the 200 milliamp, so the selectivity for hydrogen peroxide production can go to the over 92%, much better than the pure acid. And also we can also further to increase the current density. Let's say the 400 milliamp per centimeter square, only less than 3% of hydrogen peroxide can be produced as acid. But if we add a small amount of sodium, the performance the hydrogen peroxide concentration is greatly improved. And also we can compare, because hydrogen peroxide can react with the potassium magnesium. So if we can compare the differences. This one we have small amount of sodium, so the concentration is higher. So if the concentration is higher, the reaction is more faster with these chemicals to make it no color. Okay, so which means the reaction process is much more efficient. And also with such kind small amount of sodium, the stability is also improved. Normally for activity, selectivity, and stability, the 3 issues is the key issues for catalyst. So if there's no sodium, so the activity can decrease a lot. But if we have small amount of sodium, this kind of activity improved a lot. So our final target is try to real production. So we then try to develop some reactors. This is our final target, to produce some hydrogen peroxide using the chemicals continuously. Okay, so because in industry the CEM is the membrane is very important. So we use, because our system is in acid, so and this one is also in acid. So we develop such kind of reactors, and then we want to use this reactor to produce hydrogen peroxide continuously. And this is a general schematic for this process, because there is a sodium. We flow the sodium in the middle layer, and then at the if we have the electricity, so the sodium will go to the surface of the catalyst and then modify the catalyst and then give a high production rate for hydrogen peroxide. So the most importantly, this one actually we can compare, because this one can the oxygen towards the hydrogen peroxide, we can go to the 500 hours. 500 hours is more close to the industrial requirement. So this is our previous work. And also this is and also because in our version, most of the people say lab scale sometimes is small amounts. We use our device and we can produce hydrogen peroxide by using such large bucket. One day we can produce one bucket. It's very efficient hydrogen peroxide. And also we can also have the high concentration hydrogen peroxide. Because for hydrogen peroxide for disinfection, what we only use is only 0.5%, and we can easily get 2% hydrogen peroxide for disinfections. A previous work is use the small scale, is only 4 centimeter square, and now we have built 100 centimeter square the reactors. So if the active area is increased, so the production rate, the production rate and will be further increased. And actually, because hydrogen peroxide can be used for disinfections. So and this one, I saw this one in the Xuzhou airport, because this one is used for disinfections. This is hydrogen peroxide vapor. I also communicated with the admins for this one, and he told me that this is hydrogen peroxide. But this one is just directly use hydrogen peroxide inside, which means you have to purchase hydrogen peroxide first and go into this one, and then go to this vapor. So now I'm trying to working on such kind of compact equipment building, to try to build such kind of equipment by using only oxygen and using water to produce hydrogen peroxide, which means we do not need to purchase hydrogen peroxide first and then go to this vapor. So we can directly use oxygen and water. And also this is small. This is a small scale, and also we want to build such kind of equipment. So this one we are also discussing with some companies, try to make some collaborations to build such kind of device. And this is Hong Kong, in the Hong Kong Railway. This is also hydrogen peroxide. So we want to develop such kind of equipment and used for disinfection, used in agriculture to make such kind of device. And finally, I will shortly introduce a little bit of work for ammonium production, because of time limit. So we all briefly introduce the ammonium production. So we also build such kind of device, because ammonium actually we can get from the nitrogen gas, or we can get from the nitrate pollution. So in this work, we build such device and convert the nitrate waste to ammonium. Okay, so in this one, we go to the 3,000 milliamp per centimeter square, and we can also have a high selectivity, 3,000. And also by using such kind of device, we can go to the 20 amp. So the current is actually very is over the requirement of the industry. So, and we can also have a high theoretical efficiency for ammonium production. Okay, so so in short summary, so we use the middle part is building the reactors, and we use some clean electricity and convert some chemicals, convert some earth abundant molecules, including oxygen, including water, or some nitrate waste, and convert to hydrogen gas, or to producing hydrogen peroxide and also ammonium. And in addition to this one, our research group also did some work on CO2 capture and conversion, and also biomass upgrading. And finally, okay, thank you.